Now it should be okay. Yeah, so hello everybody, and I think we can start now. As you know, we have 2 talks for today, and it is my pleasure to announce the first speaker today, who is Stephan Jagau. Stephan did his PhD in economics at the University of Amsterdam in the Netherlands, and he's currently a postdoctoral researcher at the University of California in Irvine. He is also a member at the same time of a research group called Epicenter at the University of Maastricht in the Netherlands. He is mostly interested in foundational issues in game and decision theory as a theorist, but also as an experimentalist. Today, he will talk about additive context-dependent preferences. Stephan, it's our great pleasure that you are going to give this talk. As you know, you have 20 minutes, and then we have a few more minutes for questions. So please go ahead. We are looking forward to it.
All righty. Thank you. And thanks for having me today. Let me pull up my slides and then we can get started. Oh, I think I gotta share my screen first. All right. And thanks for the introduction. Maybe let me only add that I'm on the job market this season, so if you like what you see, here's my homepage, www.jagau.com. This is not my job market paper, something I've been working on for a while, and now the job market threw a bit of a wrench into finishing it, but I think I can still give you some interesting insights regarding this problem. Let me jump right into it. One disclaimer, most of the literature is going to be right at the end so that I can have enough time for sure to give you the structure of what's going on. So in case you feel like some literature is not discussed, hold up until the end. All right, so let's jump right into it. This is going to be kind of framed in a game theory way, but these preferences have other applications. So I'll say a little bit about that at the end too. But let's start with the game theoretic motivation. Now, if you do game theory experiments, like an archetypical thing that you would encounter in experiments is something like that. You have people play a game like easy game like this, Prisoner's Dilemma, in monetary payoffs. And you might observe a sizable number of subjects behave like this here. They cooperate in the prisoner's dilemma, even though for them, in terms of monetary payoffs, cooperation is strictly dominated by defection. Now we can ask, is that irrational behavior on the part of that subject that chooses to cooperate? And I would say maybe the most convincing defense you could have in for classical game theory in this case is to say, well, we don't even know what that subject's utility function is. We can't really judge whether that role player acted rationally without knowing what utility he attaches to those game outcomes. If it's not the monetary payoff by itself, we can't really say whether that was irrational or not. So then it becomes a question, how do we actually measure the utility of a game, and based on or of game outcomes and based on in-game behavior rather than something outside of the game. And well, if you just approach that kind of in a naive way, what's going on? Well, you have a matrix of utility values given all the states that in this case are opponents' strategies, or in case of multiple players, opponents' strategy profiles. And you want the player to look at the same utility values for all beliefs he could form over his opponent's behaviors. So instead of the normal primitive of just a preference relation over outcomes, over lotteries over outcomes, we're looking at some conditional object here where we have a ranking over our strategies for every strategy combination of the opponents. So we have a conditional preference relation where the conditioning goes in terms of opponent strategy profiles, Can extend this in terms of beliefs over opponents' strategy profiles, and that's the primitive going to be working with here today. So the P is any probability distribution over the opponent's strategy profiles here. Let me first give you some motivation for approaching the problem in this way. So how am I approaching the problem? Well, expected utility here is going to be studied in terms of context-dependent preferences. Context is opponent's behavior. Now, in such a setting, what happens? Well, the beliefs are the primitives. They're not going to be a consequence of the representation anymore, but they're going to be put in at the top. And it's going to be the reversals of preference across different beliefs here that give the richness to the setup and identify utility. And well, there's other ways we could look at games, right? We could look at it just in a normal savage approach at the problem. Now, what would we do then instead? We would take states and outcomes, start from a preference over all mappings from state to outcomes. Now, why is that not so attractive? Maybe there's two reasons why you might not find this so attractive. First, we have to admit many acts, and a lot of those acts are going to be inconsistent with in-game strategies. If you think of all mappings from states and outcomes to the reals, well, some of those are not going to be implementable in terms of mixed strategies in the game. So that's kind of a problem if we want to study behavior empirically and derive preferences from empirically observable behavior. And then the other thing is also, in like a savage approach, normally the utility and the beliefs are jointly determined. But here we're kind of looking at a different animal, as I already said. Those payoff matrices require a constant utility over pure strategy profiles across different beliefs. So in some sense, those conditional preferences are kind of the math that springs out of the problem, where you're already implicitly assuming, if you're looking at a game matrix, that you have all those beliefs and your utility is somehow determined across all those beliefs in a constant way. So much about why I'm doing this. Now let's look at the problem itself. So structural problems of the representation are kind of going to drive my results here. To simplify, I'm going to look at the whole problem in terms of utility differences. So take any state in the game theoretic context. That's a profile of opponents' pure strategies. Take two acts, AI, AJ. Look at the difference, AI minus AJ of utilities. I'm going to denote that as DIJ. I'm just going to look at everything in terms of those utility differences. If you think about it, that's actually a degree of freedom that you would normally exploit in game theory already, because we used to add a constant to every column of a payoff matrix. We used to multiply all those payoff matrices by constant terms, and we don't think that's going to matter. That's also not affecting the best response correspondence. So in some sense, what I'm doing here is I'm just going to filter out these degrees of freedom, and then my primitive or my representation that I'm ending with is going to be difference vectors describing comparisons between different strategies in the game, right? And each difference vector is going to be a vector in the real space of dimension equal to the size of the space of opponents' pure strategy profiles. So that immediately tells us the structural requirements behind this kind of representation. Well, first, of course, these pairwise preferences need to be represented by the representation. So if I take a utility difference at any probabilistic belief I could have about my opponent's behaviors, that difference with the inner product of the difference vector and my belief, that should be weakly positive if and only if I prefer the act I to the act J. What does that mean geometrically? Well, if I look at the indifference set, this vector is going to be normal to this indifference set. So this indifference set is either a hyperplane or it's going to be contained in a hyperplane. Okay, So far, so good. And that's something we already knew. Something that's maybe more interesting is if I now go from 2 to 3 acts, something that's revealed in the difference view that's not so clear in the raw utility view is I also need to satisfy the second condition over triples, which has been called strong transitivity in a voting kind of context. Now, what happens here? Well, the difference vector for ij plus the difference vector plus jk must be equal to the ik difference vector if we sum those up. And I call this strong transitivity because, as we're going to see, we need transitivity to get this, but it's not going to be quite enough. It's a little more than transitivity if you think about it, because you're also adding up these numerical intensities, if you will. So it's a little bit more similar to measuring distances on a line where all of those distances have to be additive. So now the question is really just how do we impose conditions on the conditional preference system to get back those structural requirements. For pairwise comparisons, that's already pretty well understood. How does that work? Well, we have our hyperplane D12 here with a comparison between Act 1 and Act 2 is a normal vector to that hyperplane. So that hyperplane is going to separate the strict preference regions on my simplex of beliefs. And that, just looking at that picture, kind of tells us all the axioms we need to get there. Of course, we need a local preference at every belief. We also need some kind of continuity where we know that between each two strict preference beliefs, if we go in between those, we vary continuously. At some point, we're going to hit an indifference. And we also need to make sure that we get a hyperplane for that indifference region. And that basically boils down to betweenness. We can take those apart, but in principle, that's what we get, right? We don't want an indifference region, but we want a line, and we also want this not to be a curve. So that's kind of what gives us the betweenness. And now what's interesting is in a lot of cases, we already get something that's ratio scale unique. So we can only choose the unit of measurement, and we're done in terms of those utility differences between 1 and 2. And that happens as soon as we have preference reversals at any point inside the belief simplex. Otherwise, stuff is only going to be ordinally identified. So the direction of each local comparison is going to be identified. And now that ratio scale uniqueness, of course, is a problem because we still have the second kind of condition, and nothing yet guarantees that the second condition, strong transitivity, is going to be satisfied. But we already have something that's ratio scale determined in a generic case based on the pairwise comparisons. Now that means we need additional conditions to extend this thing to more than 2 acts, and that's pretty similar as the strong transitivity connection already hints to something like an aggregation problem in voting theory. Now, what drives those additional conditions here at the pairwise level? You can see this very nicely, what the structure of that linear pairwise comparison is that it imposes, called this linear preference intensity. What happens here? Well, you have take any transfer vector between 2 beliefs inside the probability simplex. What happens now is, if I look at any other 2 beliefs that are related according to a scaling of that same transfer vector, so you can think about this as some kind of congruence relation with respect to, in this case, a one-dimensional subspace, well, then the preference or the utility differences, they're going to respect this, right? So if I look at this transfer vector between P and Q here, it's a scaling of this transfer T with respect to some scaling factor lambda. That's going to tell me that if I look at P minus Q and I look at the change in utility differences associated with that, it's going to be some lambda times the change associated with T. Now, and that's where additional constraints are going to come from. Let's look at how it works when we go from pairs to triples. Not going to talk much about more than triples, but structurally that's going to stay very similar, as I'm going to try to convince you at the end. Now, for a triple representation, we need that strong transitivity, as I already hinted. Now, the transitivity, raw transitivity, just on the local preferences, having transitive preference relations there, it's going to be necessary but not sufficient. Here's a nice illustration of this. You see the preferences are completely transitive across the whole belief simplex. But in this case, we get a linearly independent triple of pairwise comparisons. So we're never going to be able to satisfy the strong transitivity condition here. So now what's going on in terms of linear preference intensity here? You can nicely draw that up in the picture. Well, those linear preference intensities in this case here just don't add up. How do we see this? Well, let's take these three transfers here on the left side of the picture, the three green curves. We go from 1, 3 to 1, 2, from 1, 2 to 2, 3, and we go from 1, 3 to 2, 3. Now what happens is, as we move along here, going to be able to scale up this this transfer between 1, 2 and 1, 3. So we know that it's the same change in utility difference across those two, and I go from 1, 3 in the 1, 3 indifference to 1, 2 indifference, and here I'm going from 1, 2 to 2, 3 indifference. So if I scale this up here, I should also end up at a 2, 3 indifference point, but that just does not happen. And that's really the problem here. If everything was linear, if I move along, I scale everything up, this Q down here should also be a 2, 3 indifference point. So if we move this, we shift this 2, 3 indifference set around a little bit, we get something that is fully consistent with expected utility on the triple, and that's going to give me my additional condition in the triple case. I call that one triple additivity. How does that work? Well, we take 6 indifferences, 5 indifferences, P12, P12, P13, P23, and then P12 prime and P13 prime. And we already know that P12 prime and P13 prime and P12 and P13 are related by the same kind of transfer vector. And now we observe this additional point Q. That's where Q and P12 prime and Q and P13 prime are related by the P23 and P12 and P23 and P13 in transfer vectors. And that's gonna have to allow us to conclude that this additional belief Q has to be a 2, 3 indifference belief. That turns out to be necessary and sufficient, together with transitivity and the pairwise comparisons, for a triple representation, also with strictly dominated acts, weakly dominated acts, you name it, as long as we only have 3 acts. And what's a nice intuition here is really it's about reconciling directly observed information with indirectly implied information, right? We have those directly observed pairwise comparisons, and if you look at it geometrically, what went wrong here geometrically is those two pairwise comparisons intersect at this point. So if that was inside of the belief simplex, that should be a total indifference point between 1, 2, and 3. But the 2, 3 indifference line just doesn't go through there. If we fix that, we have something like a total indifference point outside of the probability of the belief simplex. So what happens with this condition is we reconcile those directly observed pairwise comparisons in a way that everything also smoothly works out outside of the belief simplex, and in that sense we have some indirect information, those triple intersections that reimpose some additional constraints on stuff that has to happen inside the belief simplex for our representation to work out. Now, just a little teaser, how does it work with more than 3 acts? Well, in principle, stuff works the same. Again, let's look at a situation with 4 acts. Well, now we can have more complicated situations where, for example, here we have 2 triple intersections, 1, 2, and 1, 3, and 3, 4, and 2, 4. Those already in a 3-state setup would uniquely pin down my 2-3 pairwise comparison. In this case, it would be entirely outside of the belief simplex, my pseudo indifference points here. Now, if I put a directly observed indifference point here, I'm never going to be able to reconcile that indirect information with that direct information. So in some sense, that's a similar problem. Gets more complicated, gets compounded if we have more than 2 acts, because we can make more comparisons. How can we think about that in linear algebra terms? Well, now also relations according to transfers in multidimensional subspaces are going to matter, or congruence with respect to multidimensional subspaces is going to matter, because if we go across more than 3 acts, we're going to be able to chain those up in cases that in ways that this is still informative for what happens inside of the belief simplex. We get some additional conditions too that I'm not going to really be able to get into here with degeneracy. 2 ways in which you could have degeneracy here is if only 2 states, everything's on a probability line. Then, for example, this whole triple additivity condition is going to be toothless. You could also have a total indifference point where everything kind of circles around the total indifference point in terms of the pairwise comparisons. In both of those cases, you're going to need additional conditions over and above what you have in a fully defined case, so to say, to make it work. That's somehow interestingly related to the Menelaus theorem principle. Those additional conditions are going to be exactly that equation from the Menelaus theorem that you're getting if you're going back from the ratios of sides of a triangle to having that additional that line going through the triangle. That equation is going to be what we need to put in here at the bottom in a degenerate case to make it work. So that's all I have time for about the problem. As you see, it kind of gets more difficult. That's what I'm working on right now, kind of trying to really pin down those conditions. But in principle, it's really about, again, reconciling that indirect information with that direct information from the pairwise comparisons we see here. So it's all about triple intersections, pairwise comparisons, and connecting the lines and figuring out how we can express that in terms of observed preferences. Now, let me talk a little bit about the related literature before I close. So something that this relates to at a high level, of course, is state-dependent utility. Here's some examples. Kindly Schmeidler and Winz, well-known. Wacker is well-known from '87. What happens in those papers is we look at expected utility state-dependently for preferences over act-state tuples. Now, what's different here? Well, I don't allow for any comparisons across states to be made by the decision maker. I only need local rankings over X for each state. So it's kind of a natural adaptation of something like a state-dependent utility setup to this more reduced situation where the decision maker cannot make these comparisons across states, which in this case would be the strategy profiles of opponents, but he just knows for each strategy profile or for each belief I could have over those strategy profiles, what's going to be my preference over my own strategies. Now, more
Stephan,
closely
we are
related,
a little bit over time. Reduce the time a little bit.
Okay, let me just so we have the work by Geboa and Schmeidler, of course. That's what it's mathematically most closely related to, and what I'm changing here is They look at diversified preferences for all egg quadruples. They need any permutation over rankings to occur at some belief. What I'm really doing here is I throw in those non-diversified preferences where we don't need that kind of richness. So in terms of games, what that allows me is to look at all game matrices rather than just a subset of game matrices that are diversified. Then Andres has also some work about non-diversified preferences. And what I'm really trying to do here is I'm going to move to conditions only in terms of observed rankings, whereas he looks at something like a hypothetical second preference system or conditions with respect to signed beliefs. And the hypothetical thing is kind of something you also see with Carney, Schmeidler, and Wind. So with that, let me close. So those non-diversified preferences give you rich behavioral foundations, as you see implicit in those payoff matrices. And that's, I think, what I'm going to end with in interest of the time. Here's some to be done things I want to do. And I hope we have time for some questions.
Thank you, Stephan, for the interesting talk. Given the time, I think we have time only for one question. Anybody from the audience, please?
I have a question.
Mm-hmm.
This is Pierpaolo. Hi.
All right.
But, usually when we think about, these preferences, at least the perspective of most decision theories which I don't share, by the way, is a kind of revealed preference perspective. And if you observe actions taken in a game, well, typically you do not observe those beliefs, you only observe the choice, right? So you're talking, you mention, as to be done, work with experiments. So would you somehow measure, the beliefs that you are taking as a context for the preference, or what?
Yes, thanks for the question. I think that's well, I mean, I'm still thinking about how to get to a convincing design here, but as far as I see it at the moment, that would really be what needs to happen. These reversal points across different acts in terms of the beliefs you have, those indifference beliefs are going to identify your utility differences. So if you take this to an experiment, you're going to have to ask conditional preferences, right? You have to ask people for their preference conditional on something that the opponents could do in the game. So that in some sense is very similar to what people already do when they're trying to test case-based decision theory or something like that. They use some, I think it's called, it has been referred to something like lying without lying. You kind of fix a state and then you pay people only conditional on that state. And you do that for a lot of different states. Also clearly related to the strategy method, of course.
Thank you. Thank you once again, Stephan. I think we need to move on.
Yes. Let me stop sharing my screen. Thanks for your time.